All right. Welcome to uh, application of first TDS equation. All right. So we are going to be applying the first TDS equation we derived in our previous video to solve this. All right. Said if 1 mole of Vander gas equation undergoes a reversible isothermal expansion from an initial volume of V1 to V2, how much heat is transferred in this process? So here we want to find the amount of heat that is transferred in this process if 1 mole of Vander gas equation undergoes a reversible isothermal process, isothermal expansion from an initial volume of V1 to V2. All right, we just derived that from the first TDS equation. We said that TDS is equals to what? Is equals to CV dt plus what? Plus T into the partial differentiation of P all over what? All over the partial differentiation of T, keeping V constant, the what? The V. All right. So this is what we derive. All right. Now we are now told that 1 mole of Vander gas equation. All right. You are going to note that for 1 mole of Vander gas, we have P plus A all over V square into V minus B is equals to what? RT. All right. So this is 1 mole of Vander gas. For 1 mole of Vander gas, this is what we are going to have. All right. So the next thing we are going to be doing here is we are going to make P the subject of formula. Of course, for us to make P the subject of formula, the first thing we do is we divide through by V minus B. So if I divide this equation by V minus B, what will I have? I am going to have P plus A all over what? B squared to be equals to RT all over V minus B. All right, the next thing is I'm going to move what is at this side to that side. Then P be equals to RT all over what? V minus B minus A all over what? B squared. All right, now we can see that from our TDS equation, we have the partial differentiation of T all over the partial differentiation of T, keeping V constant. So we are going to be differentiating this P here in respect to T, keeping V constant. All right, let's do that. So for us to do this, we are going to take the partial differentiation of P all over the partial differentiation of T, keeping V constant, will be equals to the partial differentiation of T, keeping V constant, of RT all over V minus B minus A all over what? B. All right, so from here we are going to be having the partial differentiation of P all over the partial differentiation of T, keeping V constant, which will be equals to the partial differentiation all over the partial differentiation of T, keeping V constant, for RT all over what? All over V minus B. Then for this side, we are going to have minus the partial differentiation of the partial differentiation of T, keeping V constant, of A all over what? All over V squared. Of course, we are going to keep V constant. So for us to keep V constant, we are going to differentiate P in respect to T. That is, our consign is on T here. So now we are going to keep R all over V minus B constant to this side. So if I move this backward here, I'm going to have this to be R all over what? V minus B. Then we are going to be differentiating T in respect to the partial differentiation of T, keeping B constant here. I hope you get this. All right. So this time we are going to be having minus the partial differentiation of A all over what? All over here we are going to be keeping B constant. So we are going to move B square to the back. So here we are going to have v square, then the partial differentiation of t. Let me put this here. So we are going to have v square, the partial differentiation of t, keeping v constant. So here our v square will be. All right. So now here you are going to see that partial differentiation of t will cancel out partial differentiation of t. That is what 1. So this will go with this. So we'll be left with r all over v minus v minus. Now the partial differentiation of will be left with 1 all over v square into the partial differentiation of a all over the partial differentiation of t, keeping v constant. So which is equals to r all over v minus v minus. Now if you want to differentiate this, you are differentiating a all over what? We are differentiating a. We are finding the partial differentiation of a all over the partial differentiation of b, keeping t constant. Keeping v constant. Definitely everything here is going to be what? It's going to be 0. So now 0 multiplied by this is going to be what? 0. And by the time we subtract this from 0, we are going to have r all over what? v minus. So now we are going to say the partial differentiation of p all over the partial differentiation of p, keeping v constant, is equals to r all over what? All over v minus p. So let me clean this part, then we complete the solution. That is, we are going to replace partial differentiation of p all over partial differentiation of t, keeping v constant, with what? R all over what? V minus. We are going to have Tds to be equals to Tv dt plus t into what? Into r all over v minus v. So r all over v minus v. All right. So from here we are going to have our Tds to be equals to Cv dt plus rt all over v minus v. All right, but don't forget, we are told that isothermal expansion, right? Reversible isothermal expansion. So for a reversible isothermal process, what happens to the T? That is, change in temperature is equals to what? 0. So the T will be equals to 0. The reason is because we are dealing with what? A reversible isothermal expansion process. So the T will be equals to 0. So if the T is equals to 0, it means Tds will be equals to C dV into 0 plus RT all over what? V minus V into what? dV. So this one here automatically becomes 0. Then Tds will be equals to RT all over V minus V dV. All right, you are going to recall carefully that Tds, dq or Tds, let's say Tds is equals to dq. So if it is equals to dq, then we can replace Tds here with dq. So we are going to have dq is equals to RT all over V minus V dV. All right, so we are going to continue this. But before I move on, I would like to explain this, what happened here further. Now, because you might be confused, how did I get 0 here? All right, let me just put more emphasis here. All right, for you to differentiate this side, what this side is saying is this. The question is saying we are going to differentiate T in respect to differentiation of T, keeping V constant. But if you look at this side, we don't have T. We don't have T here. We only have A all over V square. So A all over V square automatically becomes constant. Why? Because we don't have T. So, and anything that does not have T becomes what? 0. Because from differentiation idea, the differentiation of any constant number becomes what? 0. Please take note of that. If you have 2, it's going to be 0. If you have 3, it's going to be 0. But if you have 2s, you are differentiating in respect to s, it can never be what? 0. It's going to be what? 2. So take note of that. So anytime you are differentiating T in respect to T. Check if what you are having is not having what is at the denominator here. You understand? And you are told you are keeping V constant. Go there, check if it is not having T. If it is not having T, it means everything automatically becomes what? Zero. You are differentiating. Take note of that, because we are going to be doing a lot of complex derivation in our subsequent video. So take note of that. So let's complete this. We want to find the amount of heat. They say how much heat is transferred in this process. So that's what we are trying to find. So now, for us to get the amount of heat that is transferred during this process, we are going to integrate. And don't forget, we have, they said, from initial volume of V1 to V2. All right. So if we integrate now, we integrate both sides. We are going to have the integration of the Q to be equals to RT. That is the integration of RT all over V minus B minus B. All right. So if you integrate the Q here, you are going to get Q. All right. So we are integrating this side in respect to what? V. All right. So it means RT becomes a constant. We bring it out. So we are going to have RT, then the integration of 1 all over what? V minus B dV. Of course, you know that if you integrate 1 all over V minus B, you get what? You get the ln of, but don't forget, we are integrating the right hand side from V1 to V2. So this is going to be from V1 to V2, V1 to V2. All right. So Q will be equals to RT into, now if we integrate 1 all over V minus B, we are going to get what? We are going to get ln, sorry, we are going to get ln of V minus B moving from V1 to what? To V2. All right, by the time we do this, our Q now will be equals to RT into, then we are going to replace our V here with V2. Of course, you know the law of this kind of integration. All right, so it's going to be ln of V2 minus B minus ln of V1 minus B. Then we'll close this. And from the law of logarithm, we know that what is there, we can further write our Q to be equals to RT into ln of V2 minus B all over ln of V1 minus B. So this becomes the solution to this question. So this is the quantity of heat that will be transferred in this process. This is the amount of heat that will be transferred in this process. And this is nothing but the application of the first Tds equation. So we'll be going for the second Tds equation, and what?